everyone, I would like to welcome you to the presentation about ScaleNet, an unsupervised representation learning methods for limited information. My name is Huili Huang, and I am happy to present the work today. Let's start with the background. Deep convolutional neural networks are widely used for computer vision tasks such as image classification, recognition, and segmentation. ConvNets generally perform better when they are trained by massive amount of manually labeled data. A large-scale dataset allows ConvNet to capture more higher-level representation and avoid overfitting. However, collecting and labeling a large-scale training dataset is a very time-consuming and expensive task, especially in fields like the neuroscience and the material science area. Researchers have investigated different kinds of approaches to learn effective visual representation on limited labeled data. Multiple studies employ the data augmentation techniques such as scaling, rotating, and cropping. Transfer learning methods are implemented to learn the high-level ConvNet-based representation in limited information content. Self-supervised learning method trains the model to solve the pre-test task to learn the intrinsic visual representation that are semantically meaningful for the target task without human annotation. Self-supervised learning method not only utilize various data augmentation techniques, but also takes advantages of transfer learning to enhance the performance of the downstream task. RotNet is one of the simplest self-supervised learning approaches that capture visual representation while rotation prediction task. The 2D rotational transformation of an image is recognized by training a ConvNet model during the pre-task task. The input image will rotate 0, 90, 180, 270 degrees and label as 0 to 3 respectively. The pre-task task achieves the rotation prediction task to learn the high representation of the dataset. This method simplifies the self-supervised learning implementation and learns desirable visual features for downstream tasks. Since RotNet only affects the input image of the ConvNet, it can be combined with other architectures such as GAN or be used for 3D structured dataset. Based on this, we are interested in how to improve the performance of the self-supervised learning in the presence of limited information for current existing self-supervised learning models such as RotNet and SimCLR. The simple and efficient unsupervised representation learning method named ScaleNet based on multi-scale images is proposed in this study to enhance the performance of ConvNets when limited information is available. This study also demonstrates the capability of ScaleNet process to improve the cutting-edge models such as SimCLR. The multi-scale rotation prediction is considered as the pre-task task. The original images are contracted using the resized operator alpha to build the dataset X alpha. Each image is then transferred counterclockwise to reproduce 4 images. No rotation, rotation by 90, rotation by 180, and rotation by 270 degrees, and labeled as 0 to 3 respectively. The lowercase g is the geometric transformation that applies to the dataset X alpha. The contracted images are then fed to the ConvNet model F alpha for the rotation prediction task. A cross entropy is implemented in this study, where the loss is the loss between the predicted probability distribution over k and the rotation y. The F alpha is the probability distribution over rotation y. Taking a two-model ScaleNet as an example, after training on F alpha, the parameter learned from F alpha are transferred to another larger scale model F1. The ConvNet F1 trained the original input dataset X based on the parameter learned from F alpha. Note that the ScaleNet allows users to train more than one pre-trained model before training the F1. The ConvNet model F here can not only be the rotation prediction task, but also can be other famous representation learning methods such as the SimCLR. Here are the experiments shows the pre-text and the classification accuracy using the RotNet and ScaleNet architecture in limited information condition. The limited information is exercised using a combination of the limited CIFAR-10 data, missing corner information, and missing the color information of images. The ScaleNet noticeably outperformed the RotNet for the classification test with the limited information. This experiment shows the adjustment of the ScaleNet to understand and detect influential features with limited information that will be crucial for many fields with a lack of data. According to the result, a grayscale channel would be sufficient to achieve a comparable accuracy similar to color image. We also use Harris to detect and remove the color information of the dataset. Harris corner features are invariant under rotation, but they are not invariant under scaling. It is shown that pretext accuracy is significantly reduced by removing corner information for both ScaleNet and the RotNet. The classification task for 4K shows the Harris ScaleNet improved accuracy noticeably compared to the RotNet. It shades the fact that the parameters learned by the ScaleNet are not only rotation invariant but also scale invariant. The ScaleNet improves the ConvNet parameter by unlocking underlying features that are crucial in the classification task. The linear evaluation based on SimCLR is introduced to further confirm the ScaleNet effectiveness in the presence of limited information. Previous study demonstrated the contrastive learning benefits from larger batch size. However, training a small-scale dataset with large batch size such as 1024 and 2048 leads to the decrease in performance, even if tuning learning rate to a heuristic. The experiment in this section used small batch size to enhance the performance of SimCLR for limited data. Figure shows the linear evaluation of multi-scale SimCLR trained with different epochs and batch sizes on the CIFAR-10 dataset. This figure demonstrates the multi-scale SimCLR clearly improves the classification results with limited information. The results further assert the ScaleNet process is an effective technique for self-supervised learning algorithm with limited information, and multi-scale training can capture necessary high-level representation that cannot be learned in the existing SimCLR model. This experiment demonstrates the ScaleNet process is proved to enhance the performance of other self-supervised learning models such as SimCLR. The attention map of ScaleNet and RotNet are generated in this figure. Both models learn high-level semantic representation of image to fulfill the rotation prediction task. The attention map of the first stage of the ScaleNet and the RotNet indicate the ScaleNet catches more age information than RotNet, which confirms that the age information is of vital importance for rotation prediction task. When the model goes deeper, the ScaleNet model focuses on more specific objects, while the area of interest in RotNet are distributed uniformly. Based on the attention map in stage 3, the ScaleNet already focuses on the head of the cat and the dog collar, while the RotNet model is trying to understand the shape of the animal. The visualization results imply that the ScaleNet focuses more on the age information and specific semantic feature, which effectively improves the image classification task. Thank you for listening. For more details, please visit the GitHub link below.